the last lecture we stopped at the parabolic problem and its finite element implementation. What we had talked about is there are this alpha family of approximations which are possible. Now depending on the choice of alpha, we get something called a stable scheme or a conditionally stable scheme in when we are doing the time marching. So let us look at these definitions in a little bit more detail today. The first definition is stability in the time sense. Here the time marching scheme is stable provided that you have the two sources of error these are, one is truncation and the other is round off. The truncation error comes because of our approximation of the derivative with respect to time. We are approximating the derivative with respect to time with a difference scheme which is essentially based on truncating a Taylor series expansion of u dot t about a time, okay, with some finite number of terms. Okay, so just like we do with the expansion of any smooth function. Okay, so because of that truncation, we are introducing an error which depends on the delta t that we take from the given time to the next time. Okay, the other part, round off error, is due to the finite arithmetic that we are doing. That is, the computer can only represent numbers with certain finite accuracy. Okay, it could be single precision or double precision. So these two are the two sources of errors, and what we say that a numerical scheme is stable if the sum of these two errors, the truncation and the round off errors, are both bounded with respect to time. That is, the errors, the truncation and round off errors are bounded. Okay, that is, what do we mean by bounded? It means that as this is time, the error lies in some within some upper bound. Okay, it can go up, it can come down. What will happen is, in one step if the error builds up, in the next step it should actually decrease so that it stays within the bounds. This is what we mean by stability, that these errors do not grow with time. So this is my error at time t. Now this does not ensure that the solution is accurate. Okay, that is, the finite element solution that we have obtained at a given time station is very close to the exact one. That we cannot guarantee. It only says that yes, the errors, if they are there, they are bounded. Okay, so let's go to the next definition. Next definition is about so-called consistency. The numerical scheme is said to be consistent if, as my delta t tends to 0, okay, the solution u as a function of time, UFE as a function of time, okay, tends to the exact solution for the system. This we have to keep in mind, is that this is not the exact solution of the problem that we have, the actual continuum problem that we have. This is the exact solution of the system of equations that we have created after doing the integration with respect to space. Okay, so exact solution is with respect to the finite element discretization that we have put in. Okay, so This means that as the time steps decrease, I converge to the exact solution of the system k, as we had written as kt plus ct dot is equal to f. The exact solution of this system is what this will converge to, and it will not converge to something else. If it converges to something else, which can also happen, then the numerical scheme is not set to be consistent. Okay, so this is a very important point that we have to keep in mind, that the solution as a time step converges, the numerical scheme should be such that it ensures that I indeed do converge to the exact solution of this system, not of the physical problem that we are trying to take care of. Third definition is convergence. This we have talked about a lot when we were doing the static problem. By convergence we mean that as the time step size tends to 0, that is, as it is made smaller and smaller, the round off and truncation errors for this ODE system of ODEs, these tend to 0. Okay, so this is very important, that as the delta t tends to 0, the round off and truncation errors tend to 0, which means that my solution is both consistent and stable. Then I get that the solution then converges to the exact one. So it has to be stable plus consistent for it to be convergent. Okay. So what it says is that my solution to the system of ODEs converges to the exact solution for that system of ODE as my delta t tends to 0. Okay. Now convergence will come with another added question. Okay, how fast does it converge? As my delta t goes to 0, how fast does the error in the solution converge? That is given by the measure of accuracy. Okay, so the numerical scheme, the accuracy of the numerical scheme is essentially, when you ask for this, then you ask the question, how close is the time march scheme solution to the exact one. Okay, and this is 1, and 2, how fast does error decay with delta t. Okay, these are two very important questions that we'll ask, which means that by accuracy we mean the rate of convergence. Okay, in light of this, what we had discussed in the last lecture, there the forward difference scheme is conditionally stable and it has accuracy of delta t. It is written by Bigot. That is, the error is of the order delta t. The rate of convergence of the error is to the power delta t to the power of 1. So rate of convergence is 1. The backward difference scheme it is stable, and the rate of convergence is order delta t. that is, it is unconditionally stable, that is, for any delta t the error will remain bounded and it will converge again as the rate delta t to the power of 1. Now we had also talked of the Crank-Nicolson scheme. This is stable and the rate of convergence here is quadratic. Okay, that is, the error converges as delta t squared. Okay, so what we expect is that with larger time steps I'll get more accurate solutions if I use this one. That's what it means. Just like with a when we used higher p elements, okay, with a coarser mesh with lesser number of unknowns, we got the desired tolerance because the rate of convergence increases. So see, these are similar approaches, similar philosophies which are adopted in both spatial and the temporal solutions. Okay, so now for these conditionally stable schemes, there is the time step size should always be less than some critical time step size, and this is given by what? Critical time step size depends on the alpha that you have chosen and the eigenvalue, the maximum eigenvalue for which system? For the system that we have written here. Let me come back. For this system of equations, if I don't have the right hand side, I put a lambda here, then it would, I won't put the lambda here, I'll solve the system corresponding free problem, okay, plus or minus lambda c t is equal to 0, and from here, from this system I'll solve for this eigenvalue lambda. How do I do this? Because when there is no forcing function, then we can use separation of variables and write the solution, the temporal part of the solution is e to the power of minus lambda t and the spatial part in terms of the lambda. So this is the eigenvalue problem that we will get, and this lambda max depends on what is my k and what is my c. Okay, so in a way this depends directly on the approximation in the space. Okay, that is, as we keep on adding more and more elements to the finite element mesh, this lambda max is going to change. Okay, so depending on that lambda max, the delta t critical is going to change. So for a fixed mesh, there is a particular lambda max that you are going to get from the stiffness and the C matrix. Okay, while you change the mesh, this is going to change. So this is something that one has to keep in mind when we want to do the temporal solutions. That is, a selection of the time steps have to be done in a proper way. Okay, so let us now go with all that we have learned here to the next set of important problems, which are hyperbolic problems. And as an example, here we will take the bar that we had, the motion of the bar under an applied load. I could have an end load P, which is a function of time, and an axial load F, which is a function of space and time. Here I can put u is equal to 0 for all times, which means u as a function of time. Sorry, I will not put it like this. Let me be more specific. U at x equal to 0 for all time is equal to 0. Okay. What will I get as the boundary condition here? Here I will get EA del u del x at L t is equal to pt. Okay, so this is the boundary condition here. I will not go into these details because we have done enough of this and you can derive these things on your own now. Okay. So what do? We again go from the differential equation, multiply by the weight function at the given instant of time t, and then integrate by parts. So we'll do that again. So we had, if you remember, del x of EA del u del x plus f of x comma t is equal to rho del 2u del t squared. Okay. So I will multiply this by a w, multiply this by a w, integrate from 0 to L, from 0 to L, this is my L, this is 0, okay, and then integrate this part by parts. Remember, we are not going to do anything to this because this does not have a spatial derivative sitting here, okay. So we'll do integration by parts, and this will give me, if I go to the next one, integral 0 to L EA del u del x del w del x, okay, plus rho u double dot w dx. This is equal to integral 0 to L f w dx plus pt w at L. So this is our instantaneous weak form that we get, okay. Corresponding to this problem. Now we go ahead and do our approximation. How will we do the approximation? By again using the variation of parameters, that is u finite element as a function of x and t will be equal to sum of I is equal to 1 to n. I will put it as coefficients ai, which now becomes function of t, become functions of t into phi x. So for example, I may use again, just like we had done in the last lecture, a 2-element mesh, let's say uniform. Then our basis functions will be, this phi i's will be the standard basis functions that we had. This is phi 1, phi 2, phi 3, and UFE will be equal to A1 phi 1 plus A2 phi 2 plus A3 phi 3. So in this case, I could put n equal to 3, and what will my A1 be? A1 will come from the value of UFE at 0 is equal to 0, implies A1 as a function of time would be 0. Okay. This we will not impose it right away. We will do it when we have constructed the matrices. Then we will go and remove this part the way we had been doing and imposing the boundary conditions in the static problem. So we will continue with this representation, okay, and then do the rest. Then if I put it back in here, what will I get? I will get integral 0 to L EA sigma 1 to n. I will put now as j 1 to n, okay, aj phi j prime, prime means derivative with respect to x, plus rho sigma aj phi j, and here I will have actually into w prime, this into w dx. This is equal to integral 0 to L f w dx plus pt w at L. Now what do? We choose to construct the ith equation, choose w is equal to phi I. Okay, this actually I should be doing it phi I. Okay, so again this will give me the ith equation in terms of a dot, a double dot, and so on. Okay, so here I should have aj double dot from what we had done in the last one. Okay, so aj, yes, double dot will be sitting here, aj is sitting here, and phi j prime. So when I do this, then I will get sigma j is equal to 1 to n aj integral 0 to L Ea phi j prime phi I prime dx plus sigma j is equal to 1 to n aj double dot integral 0 to L rho phi j phi I dx. This is equal to integral 0 to L f phi I dx plus p into phi I evaluated at L. Okay. So you see that again this is in the matrix form, and these quantities are nothing but, this is my k I j, elements of the global stiffness matrix. This quantity is nothing but my, what we will call it as, elements of the mass matrix, and this quantity is nothing but elements of the load vector at the given instant of time. Okay. You see another thing, that if my Ea is a constant with time, then the stiffness matrix does not change with time. It could change for certain problems, especially where I have plasticity, or when I am doing the finite elasticity problem where the area is changing with time, then in that case Ea could change, and because of that the K could change. Here the mass matrix, again similar thing, the density could change as the material is deforming for finite elasticity, but the way we have done things in this problem, the density does not change, so even this part, the m also remains constant with respect to time. Okay. So let's now write it in a form which we know how to use. So this will be k into a plus m into a double dot is equal to f. So this is our hyperbolic semi-discrete form. Okay. What are the boundary conditions? As before, the boundary conditions are either the displacements or the forces at the ends. Now this problem will need initial conditions. Okay. So the initial conditions for such a problem, for the second order problem in time, will consist of defining what is the displacement at time t equal to 0 and what is the velocity at time t equal to 0. Now before we go ahead, let's look at how to impose this. That is, we would like UFE at x equal to 0 and U dot FE at x equal to x and 0. Okay. Now UFE would be at time t equal to 0 will be sigma I is equal to 1 to n ai 0 phi I x. Okay. Now if I am using the Lagrangian representation, then what are these AIs? These AIs are the value of UFE at a corresponding node. Okay. So AI at 0 is equal to UFE at the corresponding node xi at time 0. Okay. What we are going to do is, we are going to now impose that this is equal to U at the node xi and 0. This is one way of imposing the boundary conditions. So what we will get is essentially we will say that the initial solution is obtained by interpolating the given initial displacement using the finite element basis functions. Okay. Similarly, you will get u Fe dot at x and 0 is sigma I is equal to 1 to n ai dot 0 phi x. Okay. And again ai dot at 0 is equal to u Fe dot at the point xi 0, and we are going to force it to be u at the point u dot at the point xin 0. So we are going to interpolate both the velocity and the displacement in order to get these coefficients ai dot and ai at the initial time. So if you see that I have the values of these coefficients, the coefficient a or the unknown displacement coefficients a at time 0 and a dot at time 0. Okay. So essentially in the time marching scheme, what we will say is that the vector a at step 0 and the vector a dot at step 0 are known. Okay. So once these vectors are known, then we can march in time. That is, we will again take time step delta t, okay, such that t0 is equal to 0, t1 is equal to t0 plus delta t. I am taking uniform time steps, but you could change the time steps, and you should, if the solution shows very little activity, that is, it is very smooth with respect to time in a particular part of the time interval, I can use large time steps. But if it is showing some very sharp temporal behavior in some time interval, there I should use smaller time steps. So in an adaptive way you can choose the time steps, but here we want to be simple and keep the time steps constant. Okay. So and this way I can again have the time at station I is equal to the time at station I minus 1 plus delta t, and we want to find the solutions at each of these stations, the a dot and all those things, sorry, at each of these stations. Okay. So just like we had done in the case of the parabolic problem, now we will have to propose a different scheme to represent the acceleration term here. Okay. That is acceleration term in terms of the values and the displacements and the velocities at previous times. Okay. So there are many methods available. Primarily the ones which are very popular are the Hubold scheme. Okay. Then there is one called the Wilson theta scheme. There is one called the Newmark scheme. What we are going to follow is the Newmark scheme, because in structural mechanics this is the scheme which is very popular. But one need not use only the Newmark scheme. That is not the only scheme which is available. We could have many such schemes depending on what accuracy we want, what kind of efficiency in terms of solution of the system of equations it leads to, etc. Okay. Now you see that whatever be the scheme, if I go to my system that we had obtained here, this system will have its own features with respect to time. What kind of features? That the solution here with respect to time is going to be oscillatory. If I think of it as a spring mass system, this is the spring, this is the mass. Okay. So it should have an oscillatory behavior in time if the f is 0. If f is non-zero, we will have one part which is the standard homogeneous solution, and the other part which comes due to the f. Okay, so the forced part of the solution. Now this is something that we have to keep in mind when we are constructing the numerical solution to the system. So okay, let's go to the Newmark scheme. It is quite similar to what we had done in the Wilson theta scheme, not in the Wilson, in the alpha family of approximations earlier. So the Newmark scheme works on this principle, that the displacement vector, it is essentially component wise, at station I is given in terms of the displacement vector at station I minus 1 plus a part due to the velocity at the station I minus 1 okay, plus you will get I will explain this. Okay, this later. What does this mean? Similarly, the velocity at station I is given in terms of the velocity at station I minus 1 plus delta t into the, sorry, I should have, it should be acceleration here, so a double dot, so a double dot at station I minus 1 comma beta comma alpha. So let's put it like this. Okay, so what we have, the displacement is given in terms of the displacement at the current station, in terms of the displacement at the previous station, and the part due to the velocity at the previous station, plus the part due to this acceleration term. The velocity is given in terms of the velocity at the previous station plus delta t into a part due to the acceleration term. Okay. Now what do we have here? A double dot I minus 1 comma theta in a generic way is equal to 1 minus theta into A double dot at station I minus 1 plus theta A double dot at station I. Okay. So we have this kind of a interpolation for the acceleration, and you see that in the interpolation, when it is used for the displacement term, I have a separate value of theta. When I am using the interpolation for the velocity, I use a separate value of theta. Okay. So based on the choice of this alpha and the gamma, I will get different families of the Newmark scheme. Okay. How do I choose these families? A member of this family for my implementation? Well, stability and accuracy are the two important criteria based on which I'll have to choose. Okay. So now you see that I can write AI in terms of AI minus 1, A dot I minus 1, and the acceleration at the step I minus 1 and acceleration at the step I. Okay. So in this representation, I can write by substitution the acceleration at the step I in terms of the displacement at the step I, the displacement at step I minus 1, velocity at step I minus 1, and acceleration at step I minus 1. Okay. So I can write A double dot I in terms of the unknown AI and the knowns at the step I minus 1. Okay. Here we assume that the solution is completely known at step ti minus 1. Okay. Similarly, the velocity at step I will be given in terms of the velocity at step I minus 1 plus the part due to the accelerations. Okay. So this is how we are going to update the velocity. Here in this, the way we have done things explicitly, we do not need to use the velocity in the formulation, but the velocity has to be updated so that it can be used here. Okay. So now if I want to go and do the implementation of this, what will I do? I will take this formula here, expand it out. Okay. I will take it, expand it out, and then put it back in the equation that we got, the semi-discrete form. Okay. And I get the system of equations which will be used to get me AI in terms of what is known as the previous time step. So let us look at some choices of the alpha and the gamma, okay, which will lead to different families of approximations. So here I have written some, that here I will choose alpha and gamma will be written in terms of 2 beta. Okay, gamma is equal to 2 beta, and if I have alpha equal to half, gamma is equal to 2 beta is equal to half, this is called a constant average method, and this scheme is shown to be stable. If my alpha is equal to half, gamma is equal to 0, then I get the central difference scheme, which is said to be conditionally stable. When alpha is equal to 3 by 2, gamma is equal to 8 by 5, gamma equal to 2 beta, remember that it is always 2 beta, we get the standard Galerkin method, which is shown to be stable. Alpha is equal to 3 by 2, gamma is equal to 2, then we get the backward difference scheme, which is also stable. Okay. Now for the conditionally stable schemes, okay, where gamma is less than alpha and alpha is greater than or equal to half, which essentially corresponds, you can take the central difference scheme falls in that category. Okay. Then in that case, again as we had in the case of the parabolic problem, here in the hyperbolic problem we have a critical time step size such that delta t has to be less than or equal to delta t critical. And what is what defines the delta t critical? It is the natural frequency of the system that we have, that is of the, if I solve this problem, k a is equal to omega squared m a. So for this system, the maximum natural frequency squared, that defines the time step size. Okay. So you see that the bigger is the natural frequency, the smaller is the time step size that you have to take. Why should you do that? Because you see that the higher is the natural frequency, the more oscillatory is the solution in time as well as in space. So in time, if it is oscillatory, then I need at least the time step size to be this much in order to be able to capture this behavior. Okay. So the time step size is essentially governed by how oscillatory is the solution that my system is the worst, most oscillatory part of the solution that the system is trying to represent. Okay. And this is the philosophy that we have to keep in mind. Remember that as my mesh gets refined further and further, my maximum frequency increases. Okay, omega max increases. That is, I can now resolve in space higher and higher frequency terms. If I can resolve higher and higher frequency terms in space, it tells me that my omega max, because as my size of the problem increases, omega max also increases. And as omega max increases, I need to use smaller time steps in order to resolve these frequency components. Otherwise, my temporal error will become large, it may blow up, and then all the job that we have done in trying to do a very good approximation in the spatial regime will go out of the window. You will not be able to get accurate approximations in that case. Okay. So remember that if I am doing something in the spatial regime, that is I am trying to refine the approximation there, I have to do a corresponding job in the temporal regime. Okay. Further, there are issues that In the spatial regime, I have a rate of convergence. If I do not get the similar rate of convergence in the temporal regime, I have to ensure my time steps are small enough, that is my temporal error. My method may be stable, but my temporal error is essentially of the same order of magnitude as my spatial error, because otherwise my total error in the solution will be so large that it will get essentially overpowered by the spatial error or the temporal error, and then my solution is of no use. Okay. So this is a very, very delicate interplay which has to be done. So if possible, one can think of automatic methods of predicting the sizes of these errors and then controlling the time step and the mesh in such a way that these do come under control. Okay. So let us now go and look at an implementation of, in a generic way, of this approach. Okay. So what we do is, let's start off with this: a at step I is equal to a at step I minus 1 plus delta t a dot at step I minus 1 plus, I will put half delta t squared into, we had a double dot gamma, I minus 1 gamma. So I will put it like this, into 1 minus gamma a double dot at step I minus 1 plus gamma a double dot at step I. Okay. So from here, if I see, I will get, implies a double dot at step I is equal to, from this approximation, half delta t squared gamma into ai minus 1 minus delta t a dot I minus 1. Okay. This minus 1 minus gamma by gamma a double dot I minus 1. Okay. So this a dot is given in terms of the unknown ai at the current time and the knowns ai minus 1, a dot I minus 1 and a double dot I minus 1. So now I put this back in the differential equation that we have. So I will get, essentially collecting terms, I will get differential equation at time station I, k into k plus, I will get here 1 by half gamma delta t squared m into a at station I is equal to f bar at station I. F bar at station I will be f at station I, okay, plus the contribution of all these things. Okay. So that is a simple algebraic job that one has to do. For example, it will be plus half delta t squared gamma into m operating on ai minus 1 plus half 1 by half delta t gamma into m operating on a dot at I and plus m 1 minus gamma by gamma into m operating on a double dot at I minus 1. Okay. So this will construct, this will give me the load vector here and this, and then I invert this matrix. This matrix I'll call as k bar. So essentially, once I have this k bar ai, then I go and apply the boundary condition. That is, according to my problem, I want to force a1 at the station I to be equal to 0, because u at station at time t is equal to 0 at x equal to 0. Okay. So I will force exactly the way we had been doing in the static problem and what we had discussed for the parabolic problem in the last lecture. So enforce the boundary conditions, I would say enforce essential boundary conditions to get k, sorry, my mistake here, I'll get k double bar ai is equal to f double bar I. Okay, solve. You will get ai is equal to k double bar inverse into f double bar at station I. Okay. So I can construct the solution at time station I using all the information at station I minus 1 and the load vector at station I itself. So this I can do. Now you see there is a small problem here. When I am talking of station 1, when I is equal to 1, for this, for the station I equal to 1, I need to obtain, so when I is equal to 1, I need to know, I assume that I know a at 0, a dot at 0 and a double dot at 0. This I know, this I know, this I don't know. This has come, these two have come from the initial conditions. This is something which I don't know, because the initial condition does not give me the acceleration at time t equal to 0. So I have to start with something. Okay. In order to start with something, we do a very simple thing, that we say that m into a double dot at station 0 is equal to f at station 0 minus k into a at station 0, because a is known. Okay, implies a double dot at station 0 is equal to m inverse into f at station 0 minus k into a at station 0. Okay. So I have this formula which I am going to use in order to obtain the a double dot at time t equal to 0, and this becomes my starting value of a double dot. Use this, progress in time, get the solution. Okay. Now remember that the time step size has to be small enough to resolve the temporal behavior of the solution. So if imagine I am talking of a free vibration problem, I do not do the separation of variable solution. I use the direct approach, that is, I want to solve Ka plus m a double dot is equal to 0. Okay. If I want to solve this problem using what we have just done, which is the direct approach, I should get the oscillatory nature of the solution given the initial conditions, and the oscillatory nature of the solution should be able to represent the the frequency contents which are there. That is, the solution should be in terms of linear combinations of the natural frequencies for this system. This we know from our basic vibration analysis courses. Okay, then I should be able to resolve in time all the frequency components, because my solution in time is going to be cosine omega n t in terms of this sine omega n t. Okay, now depending on the highest frequency term which is there, I should be choosing the time step such that this is also resolved. Okay, so with this we will finish the temporal part of our approximation. We have seen how to construct the semi-discrete formulation, apply the various finite difference approaches to do the time marching in order to get solutions at various times. We have discussed the stability, convergence, and consistency of these schemes, and we have clearly given some possible schemes which can be used in a particular temporal solution methodology. In the next lecture, we are now going to shift from this set of problems. We are going to look at one set of problems that we have not discussed till now, which are again very useful to all the users of finite element methods. Users are the people who are in engineering mechanics, or in structural mechanics, fluid mechanics, or in heat transfer. Now, one set of problems which are important are the nonlinear problems. We are not going to deal with all the nonlinear problems. We are going to look at again a sample problem, and through this sample problem show how we can construct the solutions to the nonlinear problem. Okay? So this is what we are going to do in the next lecture, and that's what we'll be covering in this course.